if you have some written question on the Google Meet. So I will not go into the slideshow, but there are some mistakes in the previous uploaded notes. So if you can correct your notes, please correct it, or else I will update the notes later on. Okay, so the third part of the DC to DC converter is the buck boost converter. We call it a buck boost converter. And why it is a buck boost converter? For a buck converter, the output voltage is going to be less than the input voltage. And for the boost converter, the output voltage will be always more than the input voltage. So to compensate this type of requirement where you can either boost or it can either buck, so a new converter is introduced and we call it a buck boost converter. So the essence of the buck boost converter is you can have the output voltage, whether it's going to be, whether you want it to be lower than the input voltage or higher than the input voltage. Right. So one thing that you should notice is that the output voltage of the converter is on the negative side. So which means that the output voltage is a negative, or we call it a negative Vout or negative output voltage. And therefore, this converter is also known as the an inverting regulator. Okay, so that's basically the introduction for the buck boost converter. And the thing is, in order to analyze the converter, we have to make some assumption, which is inductor current is always continuous, and also we analyze the converter in the steady state region, not the transient region, and the average inductor current and the the average inductor voltage and the capacitor current are zero, and all components are ideal. There is no parasitic losses within the component. Okay, so this is the diagram for the, or the topology or the circuit diagram for the buck boost converter. You can see it is somehow different than the buck and the boost converter. The positioning of the the positioning of the diode, the inductor, and also the switch, and also the polarity of the diode is different. Other than that, it is still the same. The capacitor, the load, and the source is still at the same position. Right. Okay. So by changing the position of the uh, inductor and the capacitor, the inductor and the diode, uh, it is more likely similar to the buck converter. But when you change the position of the inductor and the diode, then you can get the buck boost converter. So as usual, they're going to be two mode of operation, which is during the switch on and during the switch off. So during the switch on, the inductor is connected directly to the voltage source, and the diode is in the reverse bias. So it is an open circuit for the diode, and the current will flow into the inductor. So inductor will develop its energy and also its current. And during switch off, the inductor will release its energy to the source, so to the load, but this time it's going to be on the bottom line. From the negative point of the inductor, we go into the negative of the output voltage. Hence, you will get the inverting voltage. So this is the mode, or this is the condition of the circuit during the switch on and during the switch off. So during the switch on, the inductor will store energy. Energy will develop within the inductor, and during the switch off, the inductor will supply its stored energy to the load and to the capacitor. So mathematical analysis. So we know that during the switch is closed or during switch on, the voltage of the inductor is equal to voltage of the source. So again, we will have VL equal to Vs, which is equal to L di dt. Then from there, you know that di is delta I, the current that developed within the inductor, and delta t is the time period for the switch is on. So in this case, we have a delta IL divided by dt, which is the duty cycle times the total time for one switching cycle. So in that case, we will have Vs over dt. Right. So from there, we can see or we can find what is the delta IL. So delta IL is given by Vs times duty cycle times the t over the inductance value. So this is the voltage, the current for the inductor during the switch is closed or switch on. And during the switch is off, again, V out will equal to VL. Then we still use the L di dt. And in this case, the delta I, which is the inductor, will release its energy during the switch off, which is 1 over d time the switching time, or time the time for one switching cycle. Then from there we can get that delta IL equal to V naught times 1 minus t times t divided by L. So for the switch on, we have Vs dt over L, and during the switch off, we have V out times 1 minus dt over L. Basically, these two equation looks like the same, but these two distinguished differences is the voltage source here and output voltage here, and the term of the time is dt, and this one is 1 minus dt. So for the steady state operation, you know that the net change in inductor current must be 0 for over one period. So delta IL during the switch close plus delta IL during switch open, during switch on, and during the switch off equal to 0. So when you just you add both of this equation, what you will have is you will end up V out equal to minus Vs d over 1 minus d. So this V out equal to minus Vs times t divided by 1 over d. This is the transfer function or the voltage gain of the converter, or the buck boost converter. Notice that you have a negative value here, negative sign in front of the Vs. So this is what I mean by the inverting output voltage, which is the value for the output voltage is going to be negative. Right. So the required duty cycle can be expressed by delta V naught, V naught divided by Vs plus V naught, where the duty cycle is varies between 0 to 1. Okay. So in this case, we can see that if we vary the duty cycle, for instance, if the duty cycle is 0.1, now we have the term here is 0.1 divided by 0.9. So in this case, the gain is going to be 0.11, something like that. Or if we change the duty cycle to 0.3, now it's going to be 0.3 divided by 1 minus 0.3 is 0.7. And the value for the and the value for the term d over 1 minus d is going to be 0.43. Right. That's if you use duty cycle is 0.1, then the gain will be 0.11. If you use duty cycle 0.3, the gain will be 0.43. But what happens when you increase the gain? Let's say the gain is 0.6. So what we will have is we will have 0.6 divided by 1 minus 0.6, which is 0.4. Then you will have the gain equal to 1.4. 1.5. So you can see that we take another example. Let's say duty cycle is 0.8. So we will have 0.8 divided by 1 minus 0.8, which is 0.2. Then we will have 4. So you can see that uh, the duty cycle, if it is smaller, let's say 0.1 until 0.49, then the gain is going to be less than 1. So it is above. The voltage is stepped down, it's reduced. But when you have, let's say, your duty cycle is 0.15 until 0.9, then you have a positive or a gain more than 1. So in this case, it's going to be a step-up converter, right? So what happens when duty cycle is 0.5? So at 0.5, what you have is d 0.5 divided by 1 minus 0.5. So it's going to be 0.5 divided by 0.5, which is 1. So in this case, what will happen is V out equal to Vs. So in this case, we will say that the duty cycle is unity. Or sorry, the gain is unity, which means that V out is equal to Vs in amplitude, but not in the positive or negative sign. Okay. So when the duty cycle is more than 0.5, it is in the boost mode. If duty cycle is less than 0.5, it is a buck mode. And if duty cycle is 0.5, it is a unity mode. Right. So this converter has the capability either to step up or to step down the voltage. Okay. Power absorbed by the load is the same as the power supplied by the source. Okay. So this is the waveform for inductor current, the source current, voltages, inductor voltage, diode current, and capacitor current. It is the same as the buck and the boost converter, but maybe the difference is the amplitude or something. So more or less it is the same with all converter. Okay. Now we go to the design stage of the converter. We know that the duty cycle relationship with respect to voltage output and voltage input. And we know that if the duty cycle is less than 0.5, it is going to be a step down converter or a buck converter. If the duty cycle is more than 0.5, it's going to be a step up converter or also known as a boost converter. Right. But now how to determine the value for the inductor and the capacitor? Because we know the input voltage, we know the output voltage, we know the duty cycle, and we know the switching frequency, but the passive component, which is the inductor and the capacitor, is unknown. Right, so in order to find what is the value for the inductor, we have to find what is the value of the inductor current. So we know that if the converter is ideal or lossless, we know that P out equal to P in or the source power. So from there, we can find what is the value for the resistor, the load resistor, or the value of the input voltage. It depends on what parameter that is being given. Okay. So from there, we know that the source voltage equal to the inductor voltage times the duty cycle. Why? Because this is during the switch is on, and the inductor voltage will the inductor will store energy and develop the current. So it's only happen or only appear during the switch on. Okay, and we know that from this equation, V out squared over R equal to VSIS, we can say that V out squared over R equal to VS ILD, because ILD equal to IS. And from there, we can find what is the inductor, average inductor current value. And it's given by the source voltage times the D divided by R times 1 minus D squared. So tak ada kosong kat sini. Kita lekat kosong kat sini. So R times 1 minus D squared. So this is the average of average inductor current for the buck boost converter. And to find the ripple or the IL max and IL min, again we use the same formula. IL plus delta IL divided by 2 is the IL max. IL minus delta IL divided by 2 is the IL min. Right, so in this case, we know that this is the DC component of the converter. So we have VSD divided by R times 1 minus D squared plus VS dt divided by 2L. Right, so this is the DC component and this is the AC component. So this is the derivation if you want to see how these equations come out. Basically, we want to see what is the area under the curve. So that's why we have to do the integration. But this is the source of the mathematical equation that showed here. Okay. Again, for designing converter, you have to determine or you have to know whether your converter is working in the CCM or BCM or DCM. So in order to do that, usually same as the buck converter and the boost converter, we will calculate the minimum inductance value first. Then after that, you can use two approach, which is the 25% of the inductance value. Then you will have this term L equal to 1 over 1.25 times RL min. L equal to 1.25 times L min. Or you can use the 40% of inductor, 40% of average inductor current. So in this case, we will have delta IL equal to 0.4 times delta R times IL. Delta IL equal to 0.4 times IL. Right. So you can use both method. It's going to be a different. It's going to give you a different answer, but nevertheless, just give you the CCM. And depending on what method that you've been using, there is no right or wrong, because your aim is to achieve the CCM for the circuit. Okay. And the output voltage required of the buck boost converter is given by delta V0 over V0 equal to D divided by RC times the switching frequency. Right, so this is the voltage required at the capacitor. Right, we take a look at an example. The buck boost converter has the following parameters: Vs equal to 24 volt, the duty cycle is 0.4, R equal to 5 ohm, L equal to 20 microhenry, C equal to 80 microfarad, and the switching frequency is 10 kilohertz. Okay. Usually the question will give you in a long sentence. Try to jot down the information given by the the question into this form, where you can see okay, Vs equal to 24 volt, D equal to 0.4, R equal to 5. Because many times I see that sometimes you calculate or misput the value of the load resistor or the value of the capacitor or the inductor, such that your calculation will be wrong. So in order to avoid confusion, just jot down first all this parameter that is given and find what is the parameter that it want, or what the parameter that being asked for you to find out. Okay, in this case, it gives you all the parameter for the passive R, L, and C, and also the switching frequency, duty cycle, and Vs. So what parameter it doesn't give you is the output voltage, the ripple current, the maximum and minimum inductor current, and output voltage ripple. So you have to find what is the output voltage, inductor average current, maximum and minimum value, and the output voltage ripple. So the solution is, first thing first is we know already the duty cycle, we know the input voltage, we can find what is the output voltage. So in this case, the output voltage is 16 volt, minus 16 volt. Okay. The average inductor current. Average inductor current is given by Vs times T divided by R times 1 minus D squared. So in this case, if you substitute all the value of this parameter, then you will get 5.33 ampere. That is the DC current for the buck boost converter. Now we want to see what is the inductor current ripple. So delta L is given by Vs dt divided by L. So the Vs times 24 times 0.4 times the inductance value times the switching frequency. In this case, it doesn't convert the switching frequency into time. You can use the switching frequency on the one side because f equal to 1 over t, t equal to 1 over f. So this is the ripple current, 4.8 ampere. So which is, this is the value of peak to peak value, the delta. So in order to find what is the maximum current, you know the IL, max equal to IL plus the ripple divided by 2, then you have 7.33 ampere. And the minimum inductor current, we have IL min equal to IL minus delta IL divided by 2, which is 5.33 minus 4.8 divided by 2, then you get 2.93. So in this case, what mode of operation is this converter currently on? Question. Mau apa sekarang ni untuk converter?
Continuous.
So it is a continuous conduction mode. Why? Because the minimum inductor current is more than 0. So it is a continuous conduction mode. And the output voltage ripple is direct, straightforward. We know that delta V0 over V0 equal to D divided by RC frequency. Then you have 0.01, which is 1%. So that's all for the buck boost converter. You can see that the design is the same. The formula is almost the same. Only the difference is how you analyze the circuit. And basically, if you vary the DT ratio here, then you will get the value for the output voltage to be either less than 0 or more than 0. Okay. So buck boost and buck boost regulator only use single transistor or single MOSFET or single switch. So which means that the converter itself will have a high efficiency. More you can see that the converter's efficiency is more than 90%. You can go up into 97, 98%. It is a common to have 97, 98% of the efficiency of the converter. Right, but this is due to the single switch that being used. So when you have a single switch, mean that you have you reduce the losses. When you have a less component, then you have less parasitic, less losses. Okay, and for the converter, mostly the losses of the converter focus or are associated with the switch. Then whether or not at the switch there is two type of losses. We call it the conduction losses and the switching losses. The conduction losses deal with the current that being handled by the switch, and the switching losses is dealing with the on time and off time losses of the switch. For the on time and off time losses, we will take a look better in next week's chapter, the thermal management. Okay. Because of the single transistor, if you have a higher power, mean that you're going to press the switch, or you're going to give a major task for the switch to handle a lot of power. So most of the time the switch is incapable to work efficiently when you have a high power, high current. So therefore the converter usually limited to a small voltage, a small power, 50, 60, 100 watts maximum, something like that only. Okay. At high current, the size of this component increases with the increase of component losses and efficiency decreases. Okay. So when you have a higher current, mean that the current that flows through the component is high. I mentioned in the lecture that each component has the parasitic parasitic element, which means that something that is not there, but something is there that we don't want. So this parasitic element, like a small resistor, will have an impact when a current flows through a resistor be equal to IR. So when you have a current flow through a resistor, then you will have some sort of power losses. So uh, that's why this converter usually are not capable in handling high current. When you have a high current, the switch tends to get hot easily, and if you don't manage it properly, the switch will blow out because of the heat, or because of the heat that being generated within the switch itself, in that the switch cannot uh, take out the heat within it. uh, then the heat will accumulate, then after a period of time, then the switch will be burnt. Okay. All this pre-converter, it has no isolation between the input and output voltage, uh, which is quite an disadvantage. Mean that what is the isolation? The isolation means that the input side and the output side has some sort of electrical isolation. Usually, the electrical isolation is provided by a transformer. Mean that on the input side and the output side, there is no electrically attached wire. So therefore, they will use a transformer, so that the transformer only the input current only work on the primary side, the output current only work on the secondary side. There is no electrical connection, but it is being combined, or it is being bridged by the transformer. Right. So there is isolation between the input and output voltage. And for high power application, multi-stage conversion are used, where a DC voltage is converted to AC by inverter, and the AC output is isolated by a transformer, then converted to DC by rectifier. Okay. Yeah, this is multi-stage, or which means that you have stage one and stage two. This is mostly used in the frequency converter, where the AC is transformed into DC and transformed back into AC, or DC transform into AC and transform back into DC. Because to handle a high power application, when you have a high power, mean that you have high current. High current mean that the power that being delivered is somehow hard to handle by some type of the power switch. So in order to do that, you can either increase the voltages. So when you increase the voltage for the same power, then the current will be low. But in order to do that, you need to you need to take into account the the other component as well. In this case, the capacitor, the inductor, whether it can withstand the voltage, the high voltage, or withstand the high current. Okay. So multi-stage conversion is used because we want to step up or step down in stages, so that the strength of the switch is divided into stages, where each stage you will have their dedicated switch, so that the switch is not to be burdened by the high power for the single switch. Okay, so conclusion. So today's class is very short. The conclusion. So this is the summary of the buck boost and buck boost converter. And you can see the voltage gain is given by Vs times D for buck converter, Vs divided by 1 minus D for the boost converter, and D times Vs divided by 1 over D. Uh, sepatutnya tak ada tanda sama dengan ni, tak ada kat sini. So Vs times D over 1 minus D. Nanti saya update balik lectures note ni. Okay. So for the buck converter, the output average current or the inductor average current is given by V out over R, and for the boost is Vs over 1 minus D squared R, and for the buck boost converter, the same as the boost converter. And for the minimum current, minimum inductance is given by 1 minus D times R times T divided by 2 for the buck converter, and for the boost and the buck boost converter, R R times the time or divided by the switching frequency times 1 minus D squared times D divided by 2. That's for the boost converter, and for the buck boost converter, RT times 1 minus D squared divided by 2. Right. And for the voltage ripple, for the buck converter is given by 1 minus D divided by 2 times I think divided by 8 LC frequency squared. And for the boost converter, D divided by RC switching frequency, and for the buck boost converter, D divided by C RC switching frequency. I'm not sure about this the buck converter. I think there is some mistake. I will correct the mistake later and upload the latest version for the latest note. Alright, that's all for the buck boost converter. So this is for the attendance. Do you have any questions?
Yes, doctor.
Do you have any question?
Test is going to be on Thursday, right?
Pardon?
The test is going to be on Thursday, right?
Yes. We still follow the teaching plan.
Okay, about the appendix, is it going to be labeled?
It's going to be labeled. What do you mean?
For example, the formulas for buck converter was
Okay.
labeled, and the CCM and DCM and all that.
Yes. I will give you the a label one.
Okay, doctor. Thank you.
Right. Any other question?
Yes, doctor.
Yes.
I want to ask for the first approach and the second approach.
Okay.
In the test questions, are you going to let us choose, or you'll just let us use one of them, or any is okay?
To be honest, I haven't do the test question. I'm going to do it tonight, so I have no idea whether going to be 25% or 40%, or you can choose freely. So there is no definitive answer to your question. Not yet decided, Tahir.
Okay, doctor. Thank you.
All right. Any other question? No? No question?
Sir,
Alright.
saya nak tanya.
Okay, Ain. Silakan.
Test masuk apa, sir?
Hah? Masuk apa? DC-DC converter.
Spesifik?
Spesifik flyback converter.
Apa, sir?
Saya tak decide lagi. Saya tak buat soalan lagi.
Bukan bug lah.
Maybe bug, maybe boost, maybe both. Maybe bug with CCM, maybe bug with DCM. Saya tak buat soalan lagi.
Saya tak buat soalan lagi
Ya.
Bila saya nak buat?
Bila saya nak buat, saya buat malam ni, esok hari Rabu
Ya, betul.
Esok hari Rabu malam ni saya buat, esok saya akan bagi dekat panel untuk check. Kemudian hari Khamis saya akan print, hari Khamis malam saya akan bagi kat awak jawapan dia. Bukan jawapan untuk test tau, jawapan untuk soalan awak ni sekarang.
Faham. Baik, sir. Baik.
Okay, nanti buat soalan boleh share dalam grup. Boleh lah.
Okay, faham, sir. Faham. Terima kasih. Alright.
There's a reason sebab saya tak buat soalan lagi. Kalau saya buat soalan, nanti saya akan bagi soalan tu kat awak. Sebab tu saya buat soalan last minute. That's why I make the question last minute, so that I don't give a lot of information to you guys. Alright?
Okay, sir.
Okay, any other question, guys?
Sir, kalau buat soalan tutur boleh jawab soalan test.
InsyaAllah.
Boleh Alright.
InsyaAllah. Ada formula yang diberi ke, sir? Ada formula yang tak akan diberi. V equal to IR, P equal to I squared R. The basic formula tu saya tak bagilah. Kalau formula yang berkenaan dengan buck converter, the minimum current, maximum current, the duty ratio punya calculation, semua tu saya bagi lah. Right. Any other question? No? Okay, ada soalan lagi?
Doctor,
Yes.
I have some question about the tutorial.
Okay.
Can doctor open back the tutorial answer? There's some question on the
Sharing. Eh? Okay. Which one are you referring?
doctor question 2, I think.
Question number 2. Alright.
Below a bit.
Okay.
Okay, yes. Doctor, for finding the LM,
Mhm.
no, for finding the RM, R minimum,
R minimum. Okay.
okay. In order to get R minimum means that the P naught should be maximum, right? So that we can get the smaller R.
Again? Come again? Yeah.
I mean, when we want to get R minimum,
Mm-hmm.
P minimum equal to V naught square over P minimum. Equal to divide P. So the P should be maximum so that the R minimum, R is minimum. Right? The formula. V square over P.
Wait ah. Come again. Kamu punya soalan tadi? Kalau to get the
Yes.
to get the R minimum, we should use P maximum,
Because
right?
formula R equal to V square over P, right, doctor?
Yeah.
Right?
True.
Okay. And then kita punya V sudah fix, tapi kita punya P kita boleh pilih minimum ke maximum.
True.
Yang itu. So in order untuk dapat R minimum, supposedly P should be maximum kan? To get the small value of R.
Okay, to get the smallest value of R.
Because when I see the answer means that the R is maximum. Because we're using the smallest P.
Iya, sepatutnya ya. True. Sepatutnya kita akan pakai P maximum lah. So maksud dia kat sini dia pakai P minimum
Ya.
Okay, nanti saya tengok balik solution ni. Sebab ini pun saya ambil semester lepas punya solution ni. Jadi saya tengok balik, okay?
Maybe doctor question 10.
Question 10, alright. Okay, I jot down this one first. Wait Okay. Question number 10. Alright. DC was counted, okay?
Slow down a bit, doctor. Yeah.
Okay. Which question?
Yes, B.
B. Was
C. 10C.
10C, okay.
Okay, doctor. I want to ask, in boost converter, the IL equal to I naught ke?
In the boost converter,
IL equal to I naught? Is it correct?
You mean the average current?
Yeah.
For the boost converter.
But when I find the notes, the formula is different. It's not equal.
For the boost converter, the output current.
For buck converter is same, doctor.
Yes,
The-
yes, true. But for the boost converter, I think during the switch on, then the inductor will charge, right? Okay, so during the switch off, then the voltage will be twice the voltage of the Vs plus the inductor voltage, going to be the V out. So the V out is going to be divided by the loop. So your question is your
is I not equal to IL? Yeah, my
yes,
question
yes,
is.
yes, it is the same. The current is the same.
Uh, uh, e-
Yusun, I think I got your what you are saying right now. So you're saying that the calculation and the theoretical in the lecture note is different, right?
yes, sir.
Okay, I will check about that again,
And then
and then
minimum
then
also different.
pardon?
For the IL minimum also different calculation. For question C also at the same place. Question
So
C when doing the IL minimum.
Question C, IR minimum.
Yeah.
Oh, okay.
Didn't divide by 2. Yeah, delta I.
Okay. This one is it?
Yes.
Okay. I will check later. Then I will upload it again. Kalau there is a mistake, then I will announce in the group. Okay.
Okay, thank you, doctor.
Okay. All right. Give me time to check first. And also this one. Okay. Any other question, guys? Ada soalan lagi tak? This is one.
Tak ada doktor.
Tak ada Okay. So kalau ada apa-apa soalan, you can still WhatsApp me in the group, and I will try to resolve. For Yusun, I will check again the notes and the tutorial question, and if there is a mistake, then I will announce and upload the new one. Right?
Okay, thank you, doctor.
Alright, thank you. So kalau tak ada apa-apa soalan lagi, so we stop here and see you guys on Thursday night, right? Okay, on Thursday night. Okay, bye. Assalamualaikum warahmatullahi wabarakatuh and have a pleasant evening.
Thank you, sir. Assalamualaikum. Salam.